Okay, we're talking about problem 1 on exam 1 from spring 2018. This is the thermocalculus problem. We have a van der Waals gas, van der Waals equation of state, where P, T, and V are your state variables. A, B, and R are known constants. And you're given this weird formula for U as a function of T and V, where gamma and A are constants. Part A says calculate the constant value volume heat capacity, CV, for this gas. Looking at the equation sheet, CV is defined as du dt at constant V. So CV would equal d by dt of gamma t minus A over V with V held constant. If V is constant, then A over V is also constant. The derivative of that would be 0. Gamma is also a constant, so the derivative of gamma t dt is just gamma. So our answer ought to be gamma. Part B, derive an expression for molar enthalpy as a function of T and V. So what is molar enthalpy? That is also in the equation sheet. H is equal to U plus PV, and that is going to be gamma T minus A over V plus PV. Now, PV will not answer the question because we wanted this to be in terms of only T and V. So P was actually not allowed as a variable. So we're going to use the van der Waals equation of state to substitute for P. So PV is going to equal RTV over V minus B minus A over V. And we can add these two together. I don't know if I would spend my time doing that on an exam, but might as well do that now. Alpha T minus 2A over V plus RTV over V minus B. That should be the answer for part B. Part C says set up an integral that could be solved to calculate work for the reversible isothermal expansion of a van der Waals gas as shown in the picture on the left. So reversible is one of the important terms here. Reversible work, dW is minus PdV. This is a constant temperature process. We're doubling volume. So the work, usually we define, well, at least our textbook defines work as work done on the system. So the work done by the system we could call negative. And W is integral V1 to 2V1 of P dV. We're going to have to substitute for P because we want something that depends on V only, or temperature because we know the fixed temperature. So this will be minus the integral V1 to 2V1 of RT over V minus B minus A over V squared dV. I would recommend caution because questions like this imply that you need to get an equation that could be solved. So I would ask myself, could I actually calculate this integral? Well, if I were told T, I suppose I could put T1 there, and the initial and final volumes, notice that R, B, and A are constants, so I should be able to calculate this integral. So I think that is an acceptable answer to this question.